Welcome and thank you for downloading the SteelDev podcast.
For those of you who expected Professor Bijl here, I must disappoint you. You have to deal with me in these next 2 hours. Yeah, well, we'll see after 2 hours. But her leg bothers her too much. I think she had already this injury last Monday, I think. So it bothers her too much. So she cannot be here, and she asked me to fill in. Totally unprepared, I will tell you something about what I think you should know. Okay, but let's recap a little bit of what Professor Bijl has been talking about, and me as well, because I am giving the Dutch version of this course, and she's just one lecture ahead of me. And I'll have my lecture tomorrow, Dutch lecture, so I can rehearse a little bit on your expense. Okay. Okay. Of course you've seen this, but I would like to mention them because Osborne Reynolds and Ludwig Prandtl have had great contributions to the aerodynamics as we know it today, so recent aerodynamics. And in times that people did not live too long, these guys were quite old for their for the time they lived in. So I always tell my students that when you want to get old, you have to study physics, because these guys were all physicists. And apparently, this gives you a long life. So it's about viscous flows, laminar and turbulent boundary layers. You have read all about that, maybe heard all about that from Professor Bijl. This one is a nice picture, and I'm not sure if you came across that, but it's the paradox of D'Alembert. D'Alembert was a French physicist, and he studied the flow over balls and spheres and cylinders, and he came to the conclusion that there was no drag. The force here, the resultant force, was 0. And when he did the measurements, he saw there was a drag. Of course there is, because there's friction. But the calculations he did not include friction. So the pressure here is the same as the pressure there. And if you come to that conclusion, of course there's no drag, because the biggest force that is acting here is the pressure drag. There's so much pressure drag here, more than viscous drag, that there's a very high drag force here on a sphere or on a cylinder. And so this was called the paradox of D'Alembert, because he saw that there was drag and he couldn't calculate it. Of course, in due time, people could do that, but in the time of D'Alembert, which is some 200 years ago, that was impossible. Okay, so in real life there is friction, and you will see that there is friction, but not only friction, but also pressure drag. You've seen the boundary layer, exaggerated here, but the boundary layer is this piece of the flow very close to the surface that is the result of the friction of the molecules of the air or the gas or the fluid along the surface. And that creates a boundary layer, so a thin film of air that is retarded by the friction force. Inside the boundary layer, because there is friction, we saw that if you look at how Bernoulli's law was derived, then you excluded friction. So, because in the boundary layer there is friction, you cannot calculate with Bernoulli's law. It's not valid there. Well, I will skip this because you've seen that. Osborne Reynolds. He was the guy that looked very closely to the type of flow that was in a pipe. So there is his setup. There was this pipe here with an inlet, and he put dye into the flow. And what he saw at very low flows, very low velocities, a combination of the velocity and the friction, was that there was this very nice layer of fluid going through the pipe. But when he increased the velocity, and this so-called Reynolds number was increased, then he saw that at first there was this very thin layer, very nice, and then suddenly there was this very, what we later called turbulent flow inside the pipe. And if he further increased the velocity, then this phenomena occurred earlier in the pipe. And then he came up with his Reynolds number, saying that whenever the Reynolds number, if you have two configurations, two setups, for instance, a wind tunnel and a free flight, and if the Reynolds number is constant, then the ratio of the mechanical forces, so the mass forces and the viscous forces, are the same in both situations. So you can compare both situations. Very nice, because if you want to do wind tunnel measurements and you have a certain chord and you want to replace that chord in the wind tunnel, and you don't have a big wind tunnel, so you must have smaller chords, then if you keep the Reynolds number constant, then you can compare the flows. Everything that counts for the wind tunnel also counts for the free flight. And the Reynolds number says something about the velocity times a certain characteristic length, and for wings that's of course the chord. So velocity times chord divided by something that says anything about the viscous flow. So honey, for instance, is very viscous. So this dynamic, this kinematic viscosity, nu, is very high. And gases, of course, are very non-viscous. So these ratios of these parameters, if they are constant, then you can calculate with the same forces. Very convenient for wind tunnel measurements. Here is, of course, if you look at the flow around a model, a flat plate, an airfoil, whatever, then first you have a sort of laminar flow, so very smooth layers of flow inside the boundary layer, not so very turbulent, and at a certain point, at a certain Reynolds number, you don't see that anymore, this laminar boundary layer. You see a turbulent boundary layer with a different shear force, with a different friction coefficient. And somewhere in between the laminar boundary layer and the turbulent boundary layer, there is this layer of transition. So it's a transition point, we call it in general. If we talk about airfoils, then we talk about transition point. But in fact, it's a very small area in which this transition process takes place. Okay, I'll skip this one. A little bit hard to see, but what really happens in such a small area of this transition region is that there are, in the laminar boundary layer, there are some waves at a certain frequency that later on will give you turbulence. So they're already present, and if the flow comes along over a flat plate, for instance, what you see here, then you see some wavy character. So suddenly, somewhere in this laminar boundary layer, there is this wave getting bigger and bigger and bigger, and it moves with a certain frequency. And then when this wave, this amplitude of this wave is big enough, then we have transition. And transition will not take place suddenly, but somewhere in the flow you see those turbulent spots. They call it turbulent spots, that here and there you see some small vortices coming up in the flow, And if you put a microphone inside this flow, then you would... It sounds strange, but it's really the sound that you hear. A laminar boundary layer is just a sort of small, soft whistling sound. And then if you have a turbulent boundary, it's a rumbling sound. And somewhere in between, these small vortices, these turbulent spots, give you the idea that turbulence is coming on. And that's what you see here. This is this wavy character, these Taylor-Güttler waves in the laminar boundary layer that are bigger in amplitude as the flow goes along the flat plate. And and here you see these turbulent spots, and here we have a fully turbulent flow. So there's what you see here, these turbulent spots here, vortex breakdown, turbulent spots, here these waves, Thormin-Schlichting waves. So these Thormin-Schlichting waves have a certain frequency, and this frequency depends on what kind of object it is. Flat plate is different than an airfoil. And if you would put a speaker here with a certain frequency, then you can just increase this amplitude. So this transition process can be influenced by artificial means, by generating a frequency that is just this frequency of this wave, so that it gets bigger and bigger, and you have early transition, early turbulence. But also, you can influence this wave by putting dirt on it, for instance, or grit, very small particles of dirt. That can also influence this wave so that it gives an earlier turbulence. This Ludwig Prandtl did very fine work on this subject, also on wing theory and stuff like that. Very renowned scientist. I'll skip this one. Okay. So here we have it. If you have a wing, an airfoil of a wing, then first we have this laminar boundary layer here, and then we have the transition location, and then we have turbulence here, turbulent boundary layer. And what we have seen, if you looked at the friction coefficient of a laminar boundary layer is lower than of a turbulent boundary layer. So the turbulent boundary layer is much thicker, and it has a high friction coefficient. Now, this is what you see if you put oil on a model. This is a model in the low-speed wind tunnel of our faculty. Flow comes from the right. The model is vertical. Here you see the chord location. So this is 20%, 40%, 60%, 80%. This is the trailing edge. This is the leading edge here. This is oil with a fluorescent dye in it. Yeah, thank you very much. And what you see here is the laminar boundary layer, and somewhere here you see that the laminar boundary layer stops, because here we have turbulence. And like I said, the friction coefficient of a turbulent boundary layer is much bigger. So it sweeps all the flow away from where it is at that point. So when it is turbulent here, then all the flow, all the oil is swept away and taken away to a further located exit station. So you see that from this particular oil picture, you can see that the transition location is here. So there's turbulence. Okay, it's a little bit difficult to see. Maybe I can lower the light a little bit. This is another picture. It's a more recent picture. And the flow comes from this side. This is the lower surface of, the other picture was the upper surface. This is the lower surface of a wind turbine airfoil. And you see that at a Reynolds number of 4 million, angle of -2, there's this location at, 40% of the chord. There is this transition location. The same you see here, this black area. There is the turbulent boundary layer starting towards the trailing edge. And if you, so this is again 40, but if you then go to -6, then you see the oil being swept away. Here it is. And the transition location is moving forward. So depending on, and you see that the oil is moving in that direction, and the new transition location is this one. For -6, this is about 33% of the chord. Right? So on this picture you can see that whenever you change the angle of attack, then the transition location moves. And on the upper surface as well as on the lower surface. And that depends on the form of the airfoil, on the pressure distribution. And so you can play with that, in fact, if you want to influence the drag, the total drag of the model, the airfoil, then you can do something about the transition location, because this here is the laminar boundary layer, this here is the turbulent boundary layer, and the turbulent boundary layer has a lot more drag. So in this case, because the angle of attack goes to -6 degrees, the turbulent boundary layer gets longer, so you have more drag. If this would happen on the upper surface, then you would indeed also have more drag because of the fact that you increase the angle of attack. So both on the upper and the lower surface, the transition location is constantly moving if you change the angle of attack. And this was attached flow, so there's no separation. This is just a laminar boundary layer, a turbulent boundary layer floating along the surface of an airfoil. And then what you see, if you look at the lift and as a function of the angle of attack, then you see there's a linear relation between the lift coefficient and the angle of attack. And at some point here, the turbulent boundary layer is very thick. And then if you increase the angle of attack more, then there is separation. So the turbulent boundary layer cannot follow the contour of the airfoil anymore, and it separates. It goes straight to an undisturbed situation. And then, because of the fact that the flow is not so curved anymore, so lift is, of course, that you give a velocity downward velocity on the airstream, which makes that you give an upward velocity on your airfoil. So because there is separation, the lift goes down. And in this separated region, you can also make flow pictures. And then you see something like this. This is the leading edge, this is the trailing edge. This here is the laminar boundary layer, so it stops at about 10 to 15%. And then we have a turbulent boundary layer, and the turbulent boundary layer separates, and it makes very strange, what we call stall cells. So it's a three-dimensional pattern, although it's a two-dimensional test between walls. So there's no wing or alike, but it's just an airfoil model stretched towards both the walls. So it's two-dimensional, in fact. But because of this separation process, you see all kinds of strange stall cells here developing. Okay. The majority of the flow is, of course, turbulent. Because you have, if you look at, for instance, wind turbine blades, they have a very nice surface, but they rotate through the earth boundary layer, and there are a lot of flies and bugs and so on that collide onto the leading edge, and you have a lot of roughness on there. So the initial laminar boundary layer that would be there is turbulent because of the fact that there is a lot of disturbance on the airfoil itself. What you see on an airfoil like this, a laminar flow airfoil, is that you have a favorable pressure gradient. If you have a pressure distribution along an airfoil, then at some point you have the highest velocity on the airfoil, and like Bernoulli says, high velocity means low pressure. So low pressure somewhere on the airfoil. But this low pressure has to go down, or in fact it has to go up to an undisturbed pressure somewhere behind the airfoil. So there is a not so favorable pressure gradient between the highest the highest velocity, so the lowest pressure, and the high pressure somewhere behind the airfoil. So there's an adverse pressure gradient. In fact, there is a force pushing all the molecules in the boundary layer back because of this pressure gradient. First, you help these molecules in the boundary layer, you help them, because between here, the stagnation point, and the thickest point, the flow is accelerated, velocity goes up, and the pressure goes down, so you more or less suck the molecules to a certain position. But then, behind the thickest point, there we have this adverse pressure gradient, so the molecules are pushed back. And at some point, this force, if this pressure gradient is very high, then the velocity is going down and down and down in the boundary layer, and at some point the velocity is zero at the surface, and then you have separation. And this is some process of separation. This is calculation, but in much detail. And what you see here is, in fact, laminar separation. So it's not only that the turbulent boundary layer can separate, but if you have a low enough Reynolds number, so very viscous flows, so low velocities and very viscous air, for instance, of low temperature and stuff like that, then you also have laminar separation, which means that the flow will turn turbulent somewhere in the air, not on the model, but somewhere in the air. And that is what you see here. This is a sphere, or maybe a cylinder, but then a cut of that. And you see that this laminar boundary layer is separating here, somewhere at the thickest point. And it makes a vortex. And the point is that because this vortex, this separation, is there, the flow is different. The flow is different at the upper surface and at the lower surface. And it's so much different than when this occurs here, there will not be a vortex there, and vice versa. So when this vortex is gone, then here a vortex will develop. And that's, I think that Professor Bijl showed you also this picture of this vortex, this Kármán vortex street. But if you have a long pipe standing inside in a flow, yeah, just a moment, then you will see a Kármán vortex street coming off it. And if you are in a bath, for instance, and you use shampoo, and you go like this with your finger, then you see this vortex street also developing. Yeah.
Why is there such a big difference between the flow beneath the sphere and above? I mean, because the sphere is kind of identical.
Yeah. Why is the flow so different, since it is a symmetric object? Right? So that is because it's subsonic. If there's a vortex here, then the entire flow coming here will see a different pattern here, a different pressure here than here. The situation is not quite the same, because this gives you a pressure signal that is also communicated upstream. Pressure differences go with the velocity of the sound. Okay? So as long as you're not moving with the sound velocity, then what happens here also has repercussions on this flow here. So whenever there's a vortex here, this flow will alter here so that the lower surface will see it a little bit different.
So it's supersonic, it could be the same.
Supersonic, it could be the same. If it were not, that there would be a shock wave here. But then it would be symmetrical. Yeah.
Professor Scarano, he's like researching in terms of plasma
Right.
jets, and can you like keep the boundary layer down to the object and have like a longer laminar flow? What's the purpose of plasma?
Professor Scarano is doing research in plasma, and the question is, can you have a longer laminar flow on an airfoil or on a subject doing that? Yes, in fact, it is difficult, but the problem or the challenge is more or less that if you have a laminar boundary layer, then you lose energy. If along this boundary layer floats along a flat plate, for instance, and you lose energy because of friction. So there is a certain velocity change near the surface. And in general terms, you would have turbulence then. And then the flow would go into turbulence. But if you could suppress, or if you could supply enough velocity to a laminar boundary layer, then you could probably or possibly extend it a little bit towards a longer position, a longer chord position. But it's very difficult because you've seen that the moment you have turbulence, then you can it's very difficult to go to, say, a laminar flow again. So relaminarization is very difficult. So you have to prevent that from happening, more or less. Okay, separation. So you've seen this. Here we see this process again. You see this is a boundary layer here, and you see that you lose velocity there, you lose energy, and at some point the velocity is 0 here. And the next step is that there is a negative velocity here. So you have this vortex here that gives you negative velocity, and the flow separates here from the surface.
Got a question. You know shark skin, and like how can shark skin prevent the water to build up vortexes?
How can shark skin influence the boundary layer to reduce the vortices or to increase the vortices? That is a very difficult question, since we do not yet talk about sublayers in the boundary layer. In fact, what I tell you here is that it's one boundary layer, but in reality there is a difference between the very, very small layer on the surface and the one above that, within the boundary layer. We will see something about, well, it's not the same, but we will see something about the influence of roughness on the flow, and I'll show you in a moment. It's not the same, but the shark skin works a little bit differently. So here we go, separation. This is aluminum powder in water, and what you see here is the dividing streamline. So the flow comes from this side. The angle of attack is too big, so the flow separates from the leading edge, giving all kinds of vortices. Very high drag. If you look at the wake here, very wide wake, you lose a lot of energy, and the scar in the air is very big, in fact. Right? Okay. What happens if you have separation? If you increase the angle of attack, then the velocity at the upper surface will increase as well. So will the negative pressures. So the lower pressures will go up. That's what you see here. And in this case, we see a pressure coefficient, but you think it as being a velocity or a pressure. So the negative pressures are in this case put on the up scale. So if there's a pressure is going more negative, then it goes up. So this is a pressure peak of very negative value. If you have no separation, then the velocity will go up here as floating around the model, and the drag, the pressure will go down, and then we will have this pressure distribution going towards the trailing edge. So there is a little positive pressure on the trailing edge. If there would be no friction, then this pressure would be the same as this pressure. Then at the stagnation point, the pressure would be the same as at the trailing edge. But because we have friction, it is not. So this is a little bit lower pressure than this one. Okay. So this is the pressure distribution if we would not have separation. If we would increase the angle of attack, going from this to a next angle, a higher angle, then this peak would increase as well. Then it would be like this. But then this pressure gradient, this adverse pressure gradient, so the force with which the molecules are pushed back is too big. And then the boundary layer will say, no more. I do not have enough energy. So, excuse me. So the velocity will go down, and you will see here that this is the one with the separated flow. So, and separated flow means that there is a pressure plateau. A streamline, say this is a streamline, will only be curved if there is a force acting on it. If there is no, for instance, if it moves along an object, then the streamlines are curved because the pressure gives it a curve. But if it just separates and it moves straight on, then there is no force acting on it. So it's a straight line, in fact. So what you see here is just a straight streamline, which means that you also see a constant pressure. So this is separated flow here right from the, say, the 20% chord station. Separated flow. Here we see DU91, which is a wind turbine airfoil. And if you closely look at most wind turbine blades, then you will see at the big blades around the world, I think in 60% of all the blades around the world, you see this airfoil somewhere halfway the blade. It's very, very multi-used airfoil, I would say. DU says Delft University. With an angle of attack of 0 degrees, you will see this pressure distribution. 2.6 degrees, it moves up, it moves up. You see the CP. And this is the chord position. And this is the pressure distribution for which the maximum lift coefficient occurs. And if we then look at the transition location, which can be measured, I told you that the turbulent boundary layer can be detected if you put a microphone in the flow and listen to the rumbling sound. If you go from whistling to rumbling, then somewhere there in between there is this transition location. And you can do that. And in this case we did that, and these are the transition locations. And you see that the moment you increase the angle of attack, then the transition location moves forward. From 0 degrees to, say, 9.2 degrees, transition moves forward. And at that point here, at CL max, you see there starts some separation here at the trailing edge. At 92% of the chord, there is this straight plateau here, and their separation moves. And if you go further in angle of attack, then you will see this moving forward. Like this. For 18 degrees, we have separation around 35% of the chord. Some pressure plateau here, which means that you have a lot of drag because this separation means a lot of turbulence, a lot of temperature loss, velocity loss and stuff like that. So it's a very high drag. And why in general, we do not like separation? Because a separated boundary layer can influence the flow around all kinds of stabilizers, other wings, for instance. If you have a vertical tailplane here, for instance, and you have separation at a large angle of attack, then flaps, for instance, can get inefficient because of flow separation. So in general, flow separation is unwanted. Okay, but if we look at a laminar boundary layer profile and we look at a turbulent boundary layer profile, we see that a turbulent boundary layer profile has a lot more velocity here. There's a lot more velocity here, and that's, of course, why the friction is so high. But if the profile looks like this, then there is a lot more energy there, kinetic energy, because the velocity is higher near the surface. And if you talk about negative pressure of adverse pressure gradients, so this force that push the molecules back, then a boundary layer that has this character has more energy to flow into this adverse pressure gradient, to get further on the airfoil, despite this pushing back of this pressure gradient. So, if a boundary layer is turbulent, it can reach the back of the airfoil. And a laminar boundary layer might not be able to do that. And that is because of the fact that there is more kinetic energy here. Well, if we look at the drag of an airfoil, then we see this friction drag and pressure drag, which gives you the profile drag. Okay. And now the relation with the Reynolds number. If you look at, this is in particular for this airfoil, but you see flows alike on many airfoils. So this is a good example. If you are at a Reynolds number of 300,000, which we call low, then you'll see that there's a laminar boundary layer here, and the laminar boundary layer separates from the surface, and it gives a big, thick area of distorted flow, and you see turbulence at the transition location off the surface. So somewhere in the air, where the laminar boundary layer is located, there you see this transition to turbulence. And if you go, in this case, to a higher velocity, then you will see that this point here will move forward and go right here, and in this situation, the boundary layer will stay attached, because it's turbulent. Here, the laminar boundary layer does not have enough energy to go turbulent, and it is not turbulent, so it doesn't have enough energy to go all the way to the trailing edge, and here it has. And here, at this Reynolds number, 1.2 million, then you see the transition location moving forward. So what you see here is that the angle of attack, if you increase the angle of attack, then the transition location moves forward to the nose. But if you have the same angle of attack and you increase the Reynolds number, then also this transition location moves forward. And why is that? Because these Taylor-Guttler waves, these waves in the laminar boundary layer, they get unsteady when the velocity goes up. So they create more turbulence, earlier turbulence, so that the transition location moves more forward with the Reynolds number. But not every shape reacts the same. We've seen a flat plate, we've seen an airfoil, and this is the Reynolds number here. Reynolds number is the velocity times a characteristic length. And when you talk about spheres and cylinders, then of course that's the diameter d. When you talk about a flat plate, then you talk about the length of the plate, and when you talk about airfoils, then you talk about the chord. So that's the characteristic length. And this kinematic viscosity is at standard conditions something like 15 times 10 to the power minus 6. Here we see, if you have a flat plate, normal to the flow, can be a round plate, can be a square plate, normal to the flow, and you increase the Reynolds number, so you increase the velocity, so to say, then nothing happens. The transition is somewhere here, and the separation is always at this point here. So nothing happens, it's just the same flow pattern that you see at every Reynolds number. If you look at a flat plate, then of course first the flat plate, where the lower Reynolds number, the flat plate is laminar, and here it is turbulent, and here you see this transition from laminar to turbulent. So that's 90 degrees, normal to the flow. This is aligned with the flow. If you have an airfoil, then of course at the low Reynolds numbers also this airfoil is laminar, but because there is more surface, the friction is also higher. There's more surface than here of a flat plate, right? So that's why the CD is also higher. But it shows more or less the same behavior. What you see here of ellipses and spheres or cylinders is that there's a distinct dip here in the Reynolds number relation. Here we have what we call the critical Reynolds number, which means there is a sort of boundary, and if you cross that, then suddenly the drag of a sphere or a cylinder decreases rapidly, as you see, and quite a bit as well, because this is 0.3 and this is 1.2. So that's a quarter of the original value. And this is very convenient. Why is that? That is what I'm going to tell you in the second hour. Okay. This picture shows you the effect of the Reynolds number on the drag coefficient for various objects. And we've seen the flat plate, one normal to the flow, a normal airfoil, and we've talked about the critical Reynolds number for spheres and cylinders. And let's look at this particular object in more detail. Here we see it. This is, if you cut through a cylinder, you see this. And this theta, this angle here, is going from 0 to 90 degrees. And this picture here shows us the CP, so the development of the pressure on the surface as a function of theta. Okay. At 0 degrees, where the flow bumps into the object, there we have the maximum pressure. It's the stagnation point. So that is the maximum pressure in the flow, which is the total pressure. And if you then look at Cp, so Cp is P minus P infinity divided by Q infinity, then this P is Pt, and Pt minus P infinity is also Q infinity. So this Cp is 1. So in the stagnation point, Cp is 1, because the pressure there is the total pressure. So we start here at 0 degrees, we start at 1. And then the flow moves along the surface and it is accelerated. So the velocity goes up and the pressure goes down. And that's what we see here. If the pressure goes down, then this Cp goes down as well. And if we wouldn't have any viscosity, then it would go here to a certain value of the velocity and a very negative pressure, and it would go up again, and then we would have a stagnation point here as well. Without any friction, this would be also a stagnation point. So the Cp would go like that. But because we have friction, then we have at first a laminar boundary layer developing along the surface. So it goes like this. Here it is laminar, and what happens, this laminar boundary layer cannot round this back of the object. So it moves like that. It separates from the surface. And that is what you see here. Just in front of the thickest point, somewhere here, it moves away from the surface and it separates from the object. Okay. If we see a turbulent boundary layer, then we see this behavior here. And then we see separation here. Because this turbulent boundary layer has a profile with a lot more velocity near the surface, a lot more kinetic energy. And what you see here, if you would not have any friction, then this pressure gradient is very steep. It goes from a very negative pressure to a positive pressure. So the molecules are pushed back. And if you have turbulent boundary layer, then this can cope to some extent a little bit better with this positive pressure gradient, this adverse pressure gradient. Then it moves up to, say, about 110 degrees, so like here, and then it separates. So the nice thing is that if you have such an object, which is very blunt, then if you have it, make it turbulent, then the CD, which is the result, of course, goes down. What you see here is a pressure difference. Here we see a CP of 1, so the total pressure. Here we see a negative pressure. So there is a pressure difference across this object, which means there is a pressure drag. Right? So there's viscosity here, so we have viscous drag here, but also a pressure difference between the back and the front. This is pressure drag. And this pressure drag is much, much higher than the friction drag. So whenever you have a blunt object from the back, which gives you a separated flow here, then the pressure drag is much higher. Here you see the effect. This is, say, a cable or something like a cylinder with a diameter d, and this is an airfoil, an aerodynamic shape with a thickness 10d. And the drag force of both is the same. So the drag force, the CD is of course different because this has a higher CD than this one, but the drag force, D, is CD times half rho V squared times the area. And if you do that math, then the force is from both is the same. So you can imagine that when we went from cables that were stretched between the upper and the lower wings of the old airplanes to cantilevered wings, that there was a lot reduction in drag because these cables were cylinders, causing a lot of drag, a lot of pressure drag. So you can see the difference between this one. This is a very lousy aerodynamic shape, and this one is a good one. Okay. And here you see the same. You know, if you have a car like this, a truck, a lorry, carrying containers, it's blunt from the back. Here you see the separation, very high pressure drag. And the moment you reduce this pressure drag behind the object, then the friction drag comes up, pressure drag goes down, and the result is that you have a very streamlined object with a very low drag coefficient. Right? So here you see this how it works. This one is of course a little bit difficult. If you round a corner, then your tail sweeps like this. So it's very difficult to drive. But anyway, it has a very low drag. Okay. Now, if we look at a sphere like this, yeah.
Influence this by like having air inlets in the front and then like letting air go out in the back?
So an inlet supplying air to this dead air region in the back. Yes, that is possible, although when you create an inlet, then you create also a disturbance in the outer flow, which has its own drag. And if you have an inlet with a sort of channel towards the back, then also this channel has internal friction. So the net result may be that you have a complicated, because when you have containers, for instance, then you cannot move a channel inside, you know. So the result may be that you have a very complicated structure, and which gives maybe not even a drag reduction. So, this is a point of discussion or research if you look at manufacturers of trucks, of course, because they want to reduce the fuel consumption. And when you get down this pressure drag, then you can decrease the fuel consumption very rapidly. Okay. But when we look at the sphere here, when you see that normally at a very low Reynolds number, you will see that the flow is laminar here, and here you see what happens. This laminar flow is moving like this. So this is separation here at this Reynolds number. And what you see here, at this side, the right side, there is this disturbance here at the front of the sphere. Here. And then you see something like this. What happens is that this initial laminar boundary layer is getting turbulent here, and this turbulent boundary layer can negotiate this adverse pressure gradient much better, so then it separates here. So the idea is that whenever you have a turbulent boundary layer, then the pressure drag reduces. And this is exactly what happens here. At this Reynolds number here, the flow turns from laminar to turbulent in the natural sense, right? So that's when it happens. So this critical Reynolds number, when it is exceeded, then you have a turbulent flow right in front of the thickest point, and then the flow can round this thickest point and stay attached for a long time. And because of the fact that when you have a turbulent boundary layer, this happens, by artificial means, you can also try to reduce the drag of a cylinder or a sphere. Since you need a turbulent boundary layer, you can try to make the laminar boundary layer turbulent. And that's what happened here. You make it turbulent by putting something there, and it can be a ring or whatever disturbance you have, and then it's turbulent, and this is happening. Okay. No wonder that you see a lot of applications of this phenomenon. In the first months of the golf sport, then they found out that used balls came much further than the new ones because they did not have any dimples. So the used balls had scratches and stuff like that, you know, and they had an earlier turbulent boundary layer. And they come in the first part of the flight, they came much further than the laminar stuff. So they found out that there should be something like 328 dimples, or I don't know how many, but maybe if you have nothing to do, then you could count them. and the form means these are circles, you know, but they also have octagons, and whenever it disturbs the flow in a good way, then. But okay, so this is a smooth sphere is laminar, and a rough sphere or a rough cylinder is turbulent, and it gives a lot less pressure drag. Well, you see that with baseballs as well, tennis balls, those hairy tennis balls, you know, that's the same. Okay. Well, now there's a nice application, namely the application in sports. This was an investigation when you were very young. I think you were 7 or 8. And that was, well, skating in Holland is, of course, a national sport. It's a big national sport. And we like to think that it's a very big global sport as well, but it isn't, unfortunately. But anyway, whenever there are Olympics, then, of course, the national union, they think of ways to try to get advantage over others. And this was one of the investigations. This was a guy that came to us, and this was the predecessor of our present OpenJet facility. And this is a skater, a professional skater in this case. This is a colleague of mine, Deo Veltas. This is me at a very young age. A little bit more hair. You can't see that, but I'll tell you. But anyway, what we do here is we use a stick and then a tuft to localize the disturbance at the lower leg. And this lower leg is in fact a cylinder, like the head is more or less a sphere. And what you see is that this lower leg behaves also as a cylinder. I mean, it has some some deviations from a cylinder, but all in all, it is the same blunt shape. And if you remember the fact that when you disturb the flow, that you let it go turbulent, this boundary layer, and then reduce the drag, the same goes for the lower leg of a skating suit. When, before this, so say 10 years before this, there was this Austrian guy that introduced the aerodynamic suit. So there was one piece of Lycra, and that also gave a drag reduction, because before that you had woolen sweaters and stuff like that, you know, and a very big cap. And now he introduced this all-in-one piece of aerodynamic suit. But it was Lycra. It was smooth. So the idea was, of course, that, and it existed from 1900s. I mean, this investigation that with the spheres that was done by Prandtl. So that was 100 years before that. This is a zigzag strip. And what the zigzag strip is doing is it creates small vortices, and these vortices mix the flow, so that a laminar boundary layer is going into a turbulent boundary layer, creating a lot of energy load next to the surface, right? And what you see is a drag reduction of the lower leg. And that's of course no wonder, because it works like that. This is laminar, the first part is laminar, and then when you put this on, then you disturb the flow gets turbulent, the pressure drag goes down. And here it is. This guy was this Dutchman. He skated for Belgium because he was not good enough for the Dutch team. But in fact, he was very good at Nagano Winter Olympics. So it was 1998, right? So what you see, you cannot. What you can see it here is this small strips on the lower leg and here on the cap, giving a drag reduction, right? So this guy was first, and he skated off on the 5K, so the 5,000 meters. That was the first day on a Sunday, I remember very well. First day he skated off, I think, something like 14 seconds of his personal best, which was a world record at that time. The world record lasted about, how long does it take for a 5K? Something like 7 minutes. So it lasted 7 minutes because the second one, there was a Dutchman, he beat it with the same strips and stuff like that, with I think 0.08 of a second. And the third, which was Gianni Roma, he was also record holder at that time, and he skated off, I think, something like 8 seconds of his personal best. And this is what happened. Here's the CD, here is the Reynolds number, and if you have a smooth cylinder, then in the natural sense, the drag goes down like this. So just by increasing the velocity, because we have just one cylinder, we have one situation, air, same temperature, we just increase the velocity, and by that we increase the Reynolds number. And it goes down here, so the critical Reynolds number is somewhere here. But if you take this Lycra stuff, it's material is Coolmax, then this is just a cylinder, you know? Just a cylinder to look at it. And when you take the Lycra, you go down like this. But if you look at the lower leg, the general Reynolds, the average Reynolds number of the lower leg is like this. So you have to do something to get to a low drag. Well, you can do that by taking not a very smooth cloth, but you just take cloth with roughness. And then you have these, there you have the characteristics. Rough cloth, right? Here. So there are various types of cloth that you can use to tackle the flow. The problem is that you cannot go as low as in the natural sense. So it will cost you. The moment you do it artificially, it will cost you the very low CD. So all in all, you cannot come lower than this. Yeah, there's a question? Does it also work on the human skin? The moment you do not have hairy legs, then it works. Yeah, it does. And the nice thing is, for cycling it does, yeah. Yeah. So for cycling you should have hairy legs. But what they do, because they get massaged every now and then, they just shave the legs. And that's bad. But yeah, well. You're thinking of women cycling. Yeah, yeah. Okay. Let's move on. Okay, so when you apply different sorts of cloth, then you can have this effect, you know? If we put the strips on, these zigzags, then you see something like this. Coolmax plus strips. So this is this piece of cloth here, and if you put strips on both sides of the cylinder, then you see this. Which means that you cannot go as low as this one, but across an entire range of Reynolds numbers, you are very low. So if you are a designer of this type of suits, then if you would like to use a certain roughness, then you have to know exactly what the average Reynolds number is at which they skate, for instance, to apply this one, because this one has a very peaky character. If you do not know so much about these circumstances, then you use this, because this is constant over an entire range of Reynolds numbers. All right. So, here we have the same leg, you know, and what we see here, the flows comes from this side. Here we have a laminar boundary layer. Flow moves from right to the left. Here we have the separation, right here. And here we have a turbulent boundary layer. Also, no, not turbulent boundary layer. We have the distorted flow in the wake, so vortices. And you cannot see it now, but if you look at the pictures closely, then you see velocity, you see stripes that go that way. So there is backflow in the wake because of these high vortices. There's backflow in the wake. Here's the separation line. And if we look at the leg with the strips, you see here it is. It's about, what is it, 30 degrees, something from the front. And then you see those stripes here. These are the vortices that come from the strips. And the separation line is there. So the difference is this. The upper leg, there is no strip, and then it's the same. And why don't we do the upper leg? In this case, because of the fact that it changes position so much. If you do a skater, it does like this, you know. So the lower leg is mostly in a frontal position, and the upper leg is a little bit more difficult. So that's why we put it there at the lower leg in first instance. But this is the difference, and this difference is huge if you look at the pressure drag. Well, this Gianni Roma was a famous guy, and he skated his 8.4 seconds off his world record in the Nagano Games. There he is, 6:22. So this is the gain he had relative to the year before. And if you do a calculation, what you can gain with these lower legs that have the strips is that it is about, on the total drag of the skater, it's about 4 to 5%. If you look at the skater's drag, then 80% is aerodynamic drag and 20% is ice friction. Right, so this 80%, of course, it depends on the frontal area. That's why they skate like this and not like that. So frontal area is important, but because they are like this, the legs form a very big part of the total drag. And that's why when you do something about the legs, then you can get this 3 to 5, 4 to 5% off of the total drag, which means that is 0.5 seconds per lap. A lap is about 32 seconds, so 0.5 seconds per lap without training, without anything. You don't have to do nothing for it. Right? So, okay. So, and it was a big hit. This is, of course, it's Dutch, but Holland puts the skating world on top with the strips. Zigzagging strips give skaters wings. Romme leads stayers to a new era. The Herald Tribune, speed skaters make history. Aided by technology, a 3-man pulverized Olympic record. Herald International Tribune, stripes help, and so forth. Dutch feet, borders on phenomenal. Well, it was a big success. And why was it a big success? But nobody thought of this application. It was an innovation, and it existed for many, many, many years before that, in fact. Just like the clap skates, you know, the fact that it's not all attached to your shoe, but then this one can flap. That is, well, it existed for many years, and at some point people take that up and do an application, in this case in sports. The nice thing about this application was that the aerodynamics was put on the calendar again. Aerodynamics in sports gained a lot of attention, and Nike picked that up, and for the next games, that was in Sydney in 2000, I think, yeah. Then they came up with a full bodysuit for Kathy Freeman. She was a fast woman already, of course, but then they thought of this is a full bodysuit with a certain type of cloth. And, well, that's the roughness nobody knows, of course, but they kept that secret for a long time. But of course, this is an application of the old Pruntel discovery that you have pressure drag and that you can reduce it. Okay, so if you look at skaters right now, then most of them don't use any strips. Only the Dutch, some Dutch, use the strip on the head. And why is that? Because the effect of the strips is in the roughness of the cloth already, of the suits. But and mostly it's Nike that sells these suits. But in general, they have done nothing on the head. And if you do some measurements, then there is some reducing effect still on the head if you do something about that. So it's a sphere, of course, more or less, and that it works. Okay, and then last case study, Usain Bolt. Just to show you how you calculate the effect if it works or not. Usain Bolt is a good athlete, of course. He runs the 100-meter men in world record. He's a world record holder. World record dates from 1 year ago, I think, Berlin. Okay, if we look at the effect, measured effect of these strips, or of, well, cloth, rough cloth, then it's about, on the lower legs, it's about 3 to 11%, depending on how big, how small, and so on. Strips on the caps, 0.2 to 6%. Suppose we take something like 5 to 6% drag reduction on the lower legs and apply that to an athlete as Usain Bolt, right? So here we have him. Here, this is the world record, 9:58. And mind you, you see his hands, he runs like this. Not like this, he runs like this, because that is a very low frontal area. If you run like this, then there's a big frontal area. This, you just cut through the air, you know. So all these printers do that. Okay, so here he is. And let's look at the power that he needs to get this fast, right? So here we have the air density there was, if you look at the temperature and so on, the barometric pressure, it was 120. His length is 196, his mass 86 kilos, and his total CD times S is 0.82. If you look at the drag, you can't see it well. I'll put it again here. The drag force is CD times half rho squared times S. Right? And CD times S is, in general, what you are looking for. So CD times S is 0.82. And his legs are a part of that. So it is 0.246, CD times S. So it is a sort of drag coefficient type. Right? So the distance is 100 meters, is 9.58 seconds, so the average velocity is 10.44 meters per second. That's his average velocity. And the maximum velocity, I think he gets to that in 30 meters, 35 meters. But anyway, 1044. Okay, so what is the power that he needs for the speed? The power he needs, power is work done, and work done is force times velocity, right? And in this case, the force is the drag, so drag times velocity. Okay. CD times S times half rho v squared times v. So this is the power that he puts in his velocity. Of course, he needs more power because he has to move his muscles and he has to move his legs. But this is what remains in his velocity, right? Okay. So this gives a propulsion power of 560 watts. Okay. If we reduce his drag with 6%, the drag of his lower legs, then we see like this. So this is the power that he needs, the same power. The air density is, of course, the same, and everything is the same, except the CDS of the legs, it's minus 6%. And then, what is the velocity that he gets when he has this power, and this CD times S? And CD times S appears here. It's 10.479 meters per second. So it's 9.54. So that is 4/100ths of a second better than the world record without doing anything, except wearing a suit which gives his legs a lower drag. I'm not sure if it's allowed or not, but I mean, this is a sort of calculation you can do. It's a sort of tempting calculation, also for manufacturers of suits, maybe. Right? Okay. That's it. Friday, next Friday, I think Hester will be here as well.
Please visit our OpenCourseware website for more information. Welcome and thank you for downloading this TU Delft podcast.
For those of you who expected Professor Bijl here, I must disappoint you. You have to deal with me in these next 2 hours. Yeah, well, we'll see after 2 hours. But her leg bothers her too much. I think she had already this injury last Monday, I think. So it bothers her too much. So she cannot be here, and she asked me to fill in. Totally unprepared. I will tell you something about what I think you should know. Okay, but let's recap a little bit of of what Professor Bell has been talking about, and me as well, because I am giving the Dutch version of this course, and she's just one lecture ahead of me, and I'll have my lecture tomorrow, Dutch lecture, so I can rehearse a little bit on your expense. Okay. Okay. Of course, then you can compare the flows. Everything that counts for the wind tunnel also counts for the free flight. And the Reynolds number says something about the velocity times a certain characteristic length. And for wings, that's of course the chord. So velocity times chord divided by something that says anything about the viscous flow. So honey, for instance, is very viscous. So this dynamic, this kinematic viscosity, nu, is very high. And gases, of course, are very non-viscous. So these ratios of these parameters, if they are constant, then you can calculate with the same forces. Very convenient for wind tunnel measurements. Here is, of course, if you look at the flow around a model, a flat plate, an airfoil, whatever, then first you have a sort of laminar flow, so very smooth layers of flow inside the boundary layer, not so very turbulent, and at a certain point, at a certain Reynolds number, you don't see that anymore, this laminar boundary layer. You see a turbulent boundary layer with a different shear force, with a different friction coefficient. And somewhere in between the laminar boundary layer and the turbulent boundary layer, there is this layer of transition. So it's a transition point, we call it in general. If we talk about airfoils, then we talk about transition point. But in fact, it's a very small area in which this transition closely to the type of flow that was in a pipe. So there is his setup. There was this pipe here with an inlet, and he put dye into the flow. And what he saw at very low flows, very low velocities, a combination of the velocity and the friction, was that there was this very nice layer of fluid going through the pipe. But when he increased the velocity, and this so-called Reynolds number was increased, then he saw that at first there was this very thin layer, very nice, and then suddenly there was this very, what we later call turbulent flow inside the pipe. And if he further increased the velocity, then this phenomena occurred earlier in the pipe. And then he came up with his Reynolds number, saying that whenever the Reynolds number, if you have two configurations, two setups, for instance, a wind tunnel and a free flight, and if the Reynolds number is constant, then the ratio of the mechanical forces, so the mass forces and the viscous forces, are the same in both situations. So you can compare both situations. Very nice, because if you want to do wind tunnel measurements, and you have a certain chord, and you want to replace that chord in the wind tunnel, and you don't have a big wind tunnel, so you must have smaller chords, then if you keep the Reynolds number constant, you've seen this, but I would like to mention them because Osborne Reynolds and Ludwig Prandtl have had great contributions to the aerodynamics as we know it today, so recent aerodynamics. And in times that people did not live too long, these guys were quite old for their for the time they lived in. So I always tell my students that when you want to get old, you have to study physics, because these guys were all physicists. And apparently, this gives you a long life. So it's about viscous flows, laminar and turbulent boundary layers. You have read all about that, maybe heard all about that from Professor Bell. This one is a nice picture, and I'm not sure if you came across that, but it's the paradox of D'Alembert. D'Alembert was a French physicist, and he studied the flow over balls and spheres and cylinders, and he came to the conclusion that there was no drag. The force here, the resultant force, was zero. And when he did the measurements, he saw there was a drag. Of course there is, because there's friction. But the calculations he did not include friction. So the pressure here is the same as the pressure there. And if you come to that conclusion, of course there's no drag, because the biggest force that is acting here is the pressure drag. There's so much pressure drag here, more than viscous drag, that there's a very high drag force here on a sphere or on a cylinder. And so this was called the paradox of D'Alembert, because he saw that there was drag and he couldn't calculate it. Of course, in due time, people could do that, but in the time of D'Alembert, which is some 200 years ago, that was impossible. Okay, so in real life there is friction, and you will see that there is friction, but not only friction, but also pressure drag. You've seen the boundary layer, exaggerated here, but the boundary layer is this piece of the flow very close to the surface that is the result of the friction of the molecules of the air or the gas or the fluid along the surface. And that creates a boundary layer, so a thin film of air that is retarded by the friction force. Inside the boundary layer, because there is friction, we saw that if you look at how Bernoulli's law was derived, then you excluded friction. So, because in the boundary layer there is friction, you cannot calculate with Bernoulli's law. It's not valid there. Well, I will skip this because you've seen that. Osborne Reynolds. He was the guy that looked very